I like to start the discussion of graphs by pretending for a moment that we were architects instead of computer scientists. And we're looking in and we're saying, aha, I have my floor plan here for my new apartment that I'm going to build. And ultimately, what I want to figure out is what's the best way to wire this thing up with electricity, right? That's my ultimate goal, right? Because if you don't know anything about electricity, loosely speaking, if you ignore fire code and other safety issues, as long as your wires like all connect together, then you have live electricity, right? Like, so ultimately, in the end, you have one source of electricity that comes into your house, and then the wires run to all of your rooms, and away you go. Like, you can chain one room to another, et cetera, et cetera. Again, you have to ignore a little bit of safety code if you do it badly, but like, for the moment, we're going to live in a simplified world. So we're saying, I want to pretend that I want to know the best way to wire up my house, right? What does the best mean? Maybe in this case, my goal with best is to say, I want to do it with the minimum amount of wire, right? Because you may not realize this, but electrical wire is made with copper, and copper is kind of expensive, right? So it would be ideal if I could figure out the easiest and best way to, like, if I could find the cheapest way to wire this, that would mean using the least amount of wire. Let me try that a little bit. Okay, see if that'll help. If I can find the least amount of wire to use. So here's my like nice little architecture picture. And if I take that picture and I turn it into a picture that looks something like this, right? If you look at this, and you go back up here, you're like, oh, I can see. Here's the front porch up here. And then, let's see, I want that. Yeah, here's the front porch up here. Oh, that's not what I wanted. There we go. Here's the front porch up here. And then boom, I have a little circle labeled porch, right? Here's a closet up here. Boom, here's a little circle labeled closet. So I've taken all the rooms and I've converted them to little circles. And then I've drawn a line between them if those rooms share a wall. Get the idea here? So this particular balcony shares a wall with bedroom 1. Bedroom 1 shares a wall with this closet. Bedroom 1 also shares a wall with bathroom 2 and this hallway, et cetera, et cetera. You get the idea? We call this a graph, right? In this case, I'm calling it the wireability graph. Wireability is my word. Graph's the nice computer science term for what kind of data structure this is. But this is called a graph. And the idea of a graph is it has what we call nodes or vertices. So let's see here. So let's write some stuff down. So we have nodes / vertices. Same thing, nodes, vertices, node, vertex, right? Same concept, it's the circles. And then we also have edges, right? So we would say that this is a vertex and this is an edge, right? So an edge connects vertices, and depending on what you're representing with this will change like what's what. But in this case, we're saying that our vertices represent rooms and our edges represent if those rooms are adjacent to each other, if they share some sort of connecting wall. I call it wireability because if I'm dealing with an apartment of some kind, I'm saying, oh, if these things share a wall, that means that I could, if I wanted to, wire them together, right? I could run a wire through this wall and then balcony and bedroom 1 would be connected, right? But I can't run a wire directly from balcony to the utility room because they don't share a wall, right? Looking at the original picture here, the utility is up here, balcony's down here. Like there's no, like, I'm not gonna run a wire through the middle of my hallway, right? Like it doesn't even make sense to try and do that. So they're not directly connected, right? So I have nodes / vertices, and I have edges. So that's the first important thing to note, is that a graph is a collection of nodes and edges, right? So if you have a collection of nodes and edges, we call it a graph. There's all sorts of things that this could represent, but for now, let's just go with the simple thing. Edges, depending on what you're doing, could be directed or undirected. In this case, we're going to say it's undirected. And what I mean by undirected is the fact that there's an edge between the closet and the bedroom, there's nothing implied by whether you can go from the closet to the bedroom or the bedroom to the closet. It's the same thing either way. Like there's nothing implied. But if I were to do, let's say, a graph of intersections and roads, right? So nodes would be intersections, edges would be roads, like in some sort of city. Well, some roads might be one way, which would mean that that particular edge only goes one direction, right? Do you get the concept there? So in some cases, depending on what I'm trying to represent with a graph, edges could be directional, meaning they go from one way to another and not backwards, or they could be, in this case, undirectional, which means like, it doesn't matter. Like the fact that they're connected just means that they're connected, right? Let's see, what else? I'll make sure I cover here. A path. Okay, so let's see here. So let's write the word path down just so we can make sure we've noted it. Path. A path is a sequence of nodes and edges that are connected. What I mean is, if I say, I could look at this and I say, what's a path from the balcony to the utility room? You could say, oh, a path from the balcony to the utility room. I could go from the balcony to the sitting room, to the dining room, to the kitchen, to the utility room. That's a path. I could also say, oh, another path. Whoops, sorry, there's a, how much can you see versus? Oh, you can see the gray this year. Last year, the projector was so bad, they couldn't see the gray connection line, so I had to redraw it, but let's draw it just to make it there. Okay. Another path I could point out is I could say, aha, there's a path from balcony to the utility room, but going balcony, bedroom 1, closet, bedroom 3, bedroom 4, porch, storage unit, and utility room, right? That's also a valid path. So a path is just the path between two different nodes along edges, right? And in this particular graph, there's a lot of different paths to get between the balcony and the utility room, right? Like some of them are not great paths, but they're all paths. So that's just a path. Last thing. Nice concept called degree. When I say that I want to know the degree of a node or a vertex, what I mean is I want to know how many edges go out from it. So for example, the degree of the hall is 1, 2, 3, 4. There are 4 nodes going out. So I say, oh, the hall has degree 4, just some terminology. The balcony has degree 3. The utility room has degree 2. The dining room has degree 3, right? It's just an easy way to it's just a term to be able to say that. Okay, so that's some terminology, and let's dig in and do some more interesting stuff with this. So I'm gonna update my graph a little bit. So it's the same graph, except this time I've added numbers on the edges. And that number, we'll call this the cost of that edge. In this case, if I'm doing my apartment, I'm saying, oh, if you need to connect bedroom 1 to the closet and you want to use this wall, you need 2 meters of wire, right? Most of these numbers are made up, but like, okay, 2 meters of wire, right? If you want to connect the balcony to the sitting room, that needs 5 meters of wire, right? If you want to connect the sitting room to the dining room, that needs 5 meters of wire, right? If you want to connect bathroom 1 to the porch, that needs 2.5 meters of wire. Do you see where I'm going with it? So now I have a graph, and it shows all my rooms. It shows all the connections that could happen between rooms, and now I tell you the cost of each of those connections, right? So if my goal is to make sure that there's electricity to every room, well, then I don't actually need to put in all of these connections, right? Like if I dropped this connection here, every room would still have electricity, because electricity flows as long as there is some path from the source to the destination, right? So if I were to just kind of arbitrarily pick and be like, I don't know, this particular place, the electricity comes in here in the utility room, right? Well, then as long as there is, if I want to know, is this bathroom connected to electricity, as long as there's a valid path from the utility room to the bathroom, then we're good to go, right? So that means I don't actually need every edge. Do you see why I say that? Like if I kill this edge, nothing changes, right? Because there's still a path from here to here, from here to here. You don't have to have this path for things to be connected. So in this particular case, if I'm trying to minimize the cost, what I really want to know about this graph is, okay, here's all the connections I could make. Which ones should I make that guarantees every node is connected in and that uses the least amount of wire possible? That's what I want to know. So there's some terminology in there that I just threw out there. There's this concept of connected, right? We say 2 nodes are connected if there's some path between them. So I could say, the sitting room and the porch are connected as long as there's any path between them. And there is in this particular graph, right? As long as there's any path between them, then I say that those are connected. right? I say that a graph, so connected for nodes. I say that if I say that a graph is connected to graph, then what I mean is that there's a path between every node and every other node in the graph. There's some way to get between every node in the graph. Nobody's like disconnected. Now the big magic term for our architecture here. The minimum spanning tree. Ooh, there's a word we know. Tree. That's an interesting thought. We'll come back to that thought. The minimum spanning tree is if you have a graph like this, I figure out what's the minimum set of edges, meaning they have the least cost, the least amount of wire, that fully connects this graph. The minimum tree that spans the whole graph is what we call it. Okay, in this particular case, here's one. Right. So it's the same set of edges, just I've removed some of them. So for example, storage to bathroom is 1.5, storage to bathroom is 1.5, right? But it just so happens that in this case, this is the minimum set of edges that would be required to fully connect this graph. If you stare at it, do you kind of see what I mean when I say that? Like, you'll have to believe me that this summed up set of edges is the smallest amount of wire, but we'll talk about some algorithms you could use to find this. But if my electricity came in here at the utility room, and my goal for being connected means that everybody has a path to the utility room, then they do, right? There's a way for everybody ultimately to get to the utility room, right? But it's interesting to note that there's, like if you say this, like it's not like there's multiple ways, right? I don't have a lot of redundant connections here. If I want to go from the dining room to the utility room, there's really only one way. These connections are gone because I don't need them. I don't need them in order to have my minimum spanning tree for everybody to be connected. So this is one thing, for example, that I might want to know about a graph, right? So we're talking about graphs as a general data structure. We'll talk more about some problems you could solve with them as we move on. But here's one potential problem, right? You give me a graph with all the possible connections and their costs, like this, and I can give you the minimum spanning tree, the minimum set of edges that fully connect it. Why is that useful? Well, here's a case, right? This is a nice situation. Oh, now I know how to connect my house that has like the least amount of wire. I can save money, right? There's a lot of problems in the real world that can be represented by graphs and algorithms we can run on those graphs to come up with answers that might actually be useful, right? So this is one example. This is called the minimum spanning tree problem. Another problem we'll do a little bit later is called the shortest path problem. The shortest path problem is something you might use on a regular basis, right? What if we built a graph, as I mentioned before, where the nodes were intersections and the edges were roads, right? Well, if you wanted to know how to get from one place to another in the shortest amount of time, wouldn't it be nice if you could just feed that into an algorithm and it would spit out the shortest path from one place to another along all the roads? Maybe the cost on the edges, the lazy approach would be to say, oh, the edges are roads and the cost is the distance, right? I want to find the minimum distance. But that's not really the best reality, right? You don't really want to know the minimum distance. What do you really want to know? If I'm having you find the shortest path between two places. Time, I want to know time, right? This is where I think companies like Google and Waze really make their money, right? They have live updates so they can tell you how long it takes to get between two different nodes on a particular edge. And so when they're building the minimum path, they're not building it based simply on distance, they're building it based on time. That's what people really want. And so a modified version of a graph algorithm for the shortest path is what's used whenever you map a route in Google Maps or Waze, right? They build a graph of like the road networks, and then they run a shortest path algorithm to find you how to get from where you are to where you want to be, right? So that's an example of a real world usage of this. But all right, let's just keep going. So let's go back to the shortest path algorithm idea. Let's pretend we have a graph like this one on the left, right? We have nodes and we have edges. And what I want to be able to know, oh yeah, that looks fine. Okay, what I want to be able to know is the minimum spanning tree, right? There's two different algorithms that we classically use for this. And this stuff is old. That's the interesting thing about graphs, is like, it's not like these are some sort of modern invention. This first algorithm was created in 1956, right? This was, so I mean, we're talking about, man, what, 75 years ago-ish, right? Was a lot of the initial work on graphs. It's also a fun side note, graph algorithms are some of the fastest and most optimized algorithms in computer science, simply because they've been studied for so long. In a lot of fields, people take problems that don't look like graph algorithms, they figure out how to turn them into graph problems, and then they solve them using algorithms that were invented 75 years ago, because it's faster than anything we can do like in other ways today. So graphs are just interesting in a lot of ways. But okay, so the first algorithm is called Kruskal's algorithm. It's named after the guy who invented it, named Kruskal, right? So the idea is if I have a graph like the one on the left, and I want to find the minimum spanning tree, I want to find the minimum set of edges by cost that makes sure the graph is fully connected. Here's one approach, right? Okay, so it says draw the graph without any edges, so just the vertices. Okay, we can do that. Zoom out a little bit. I've already done it here. Boom. There we go. See if I can get both on here as best as possible. Perfect. Draw the graph without any edges, just the vertices. Sort all the edges by weight in ascending order. Okay, so I'm going to sort all these edges by weight in ascending order. All right, here we go. What's the smallest edge? What's its value? 2. And which one? Okay, so I'm going to write DE. Then I'm going to write BC. Okay, so I'm going to cross that off, cross that off. Okay, well, who's next? Okay. AC. Okay, who's next? CG, BF. Okay, CG, BF. Great. Next. CF. Okay. GF. BD. Or EF. And then EA. And DC. Great. Okay, so we've sorted the edges by weight in ascending order. So the smaller edges to the left, bigger edges to the right. Okay. So now we get here. Right? I love this description because you're like, while there are edges left, we don't have a minimum spanning tree. Gee, that kind of feels like the condition for a while loop. Ooh, you know, you could imagine building this. Okay, select the smallest edge. So smallest edge is going to be the one here, right? Check if adding this edge to the graph would create a cycle. Ooh, a cycle, that's a new word we haven't done before. What's a cycle? I'll describe it as we go. Okay, so first thing, I get the smallest edge, check if it creates a cycle. It doesn't yet. When we get to one, I'll describe it. Then we add the edge to the graph. Okay, so the edge here is DE. Okay, great, so I'll go DE. Boop. I'll add that one. That has a value of 2. Okay, I've added my edge, right? Cross it off. Boom. Okay, BC. I'm going to add that one as well. It also doesn't create a cycle, but again, I'll just find cycle in a moment when we get to one. AC. Okay, so that adds this edge here. 3. Boop. CG. Okay, CG. Boop. 4. BF. Okay, BF. 4. Okay. CF. Okay, now we finally get to the idea of a cycle, right? If I add CF, boop, what that does is now I've created what's called a cycle. A cycle means that there's a path, C, that goes out and back to itself without ever going over the same edge twice. Another way to think of it is, sorry, let's get that rehooked up. Another way to think of a cycle is just, kind of rhymes with circle. So it's you create a circle in the graph, right? It doesn't always look like a circle, but basically a cycle is, there's a way that I can trace around the graph and get back to myself without ever going over the same edge, you know? So like at this stage, adding this new edge, CF, would create a cycle because I could go CB, C to B to F, and then back to C. So that's a cycle. So we say, nope, don't add it. That's what the algorithm says. So don't add that one because it would create a cycle. So no CF. Okay, GF. Does that create a cycle? Yeah, if I add something here, right? Well, then all of a sudden I've created a cycle. Right, so, okay, don't add that. Okay, so no GF. Boom. BD, does BD create a cycle? No cycle, right? No new circle, no nothing like that. So that one's got, oh, I almost can't read it, 6. Yeah, that creates 6, okay? And now, well, there's two aspects to this. One is, if you look at my while loop condition, it says, while there are edges left and we don't yet have a minimum spanning tree, but do I have a minimum spanning tree? Yeah, I'm done. Like, you look at the graph and it's like, all the nodes are now connected. There's nobody who's not there, right? So I'm done. But even if you don't do that check, you can keep running the algorithm. So I could be like, oh, should I add EF, right? Should I add this node here? No, that would create a cycle, right? So don't do EF, right? Should I add BA? Should I add this edge here? No, that would create a cycle. So don't add BA, right? Should I add AE here? No, that would create a cycle, but that's a weird one. So let's look at it, right? Say you kind of draw this, you're like, oh, can I add that? Does that create a cycle? You might stare at it and be like, it doesn't quite look like it, but it does, because I could go here, 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 and then back, right? But if you look on the picture, it doesn't quite look like a cycle. That's why my approximation by saying, oh, it creates a circle in the graph. This one doesn't really create a circle if I draw it that way. But if I draw it a different way, then you might see it a little bit better. Here's my flaw. I should not have made that a dashed line. It makes it harder to erase. Okay, there we go. But if I were to draw the AE edge like this, then you might be more quick to see that, like, oh yeah, here it is, right? There's the circle, right? So you can't just use the circle idea, but it's just the principle that if adding that edge means that you can walk around and come back to yourself from any spot in the graph, then that's a cycle and we're no good. Okay, so I would not add AE because that would create a cycle. And I would not add DC because that would create a cycle. So I'm like, oh, great. I'm done, right? So boom, I have a minimum spanning tree. Now, minimum spanning trees are not necessarily unique. What I mean is, for a given graph, it's possible there's more than one minimum spanning tree. And in this case, this is a minimum spanning tree, and the cost is the sum of all the edges. So I go, what's my cost here? 2 plus 6, 8 plus 4 is 12, plus 2 is 14, plus 4 is 18, plus 3 is 21, so my cost is 21, right? It is possible, although I don't think it's true in this graph, but it's possible that in some graphs, there could be more than one minimum spanning tree that have the same cost. They would just have different edges. Sometimes certain edges can be swapped out for other ones, still connected, doesn't matter. So minimum spanning trees are not necessarily unique, but they are like minimum, right? There could be more than one. For the most part, if there is more than one, no one cares as long as you find one of them, right? Like, it would be very uncommon to ever have the issue of like, oh, I need to find all the minimum spanning trees. No, probably not. People probably just want one. Just give me one and we're fine, right? So there we go. So this is called Kruskal's algorithm, right? This is one approach to finding a minimum spanning tree. Now, this is an effective algorithm, but there's a small problem with it when it comes to implementing it. And by small problem, I just mean like, this one's a real pain in the butt to implement. So on Tuesday, we're going to implement a different minimum spanning tree algorithm, not this one. And the reason's pretty simple. This line right here, that is really, really hard to implement in code. I mean, not really hard in the sense that like no one knows how to do it. Of course we know how to do it. It just kind of sucks. Like building this in, you're like, that's really annoying. If there's no cycle, detecting if there's a cycle in the graph is kind of a painful and not like, it's a slightly complex operation, meaning it takes more time than we would like. So because of that, there are tricks to make Kruskal's algorithm work. And if you go online, you're like implementing Kruskal's algorithm, you'll find like nice implementations of it and good explanations. But in the end, you watch the explanation, you're like, that kind of sucks. Like, I don't really want to build that. I'm surprised anybody wants to build that, right? So this particular line makes it difficult. So it's not like this is a perfect algorithm, but like it gets the job done. Let's look at another one that is equally good at finding the minimum spanning tree, but is a little bit less complicated. Prim's. Okay, here's Prim's algorithm. 1957. So Kruskal's was 1956, Prim's is 1957. You can imagine like people were working on this particular problem at that time, and here was two of the leading approaches. So here's Prim's algorithm. Draw the graph without any edges, same idea. Choose an arbitrary vertex, so an arbitrary node, and add the smallest edge that's going out of it. And then while we don't have a minimum spanning tree, keep adding small edges until you do, right? And what I mean by keep adding small edges until you do is you look at the connected graph you've built so far, and you find the smallest edge that can go out from that connecting graph. We'll do it as we go here. Okay, so here's Prim's. So I'm going to pick an arbitrary vertex. And I'm going to pick an arbitrary node. Jeremy, give me a node, A through whatever the highest letter is. D. Okay, so we're going to start here at D. The algorithm says pick the smallest edge going out from D. Okay, what's the smallest edge going out from D? 2. So I go, great, D to E is 2. Done. Now I'm building my minimum spanning tree one piece at a time. So I'm like, ooh, I have the start of my minimum spanning tree. It isn't finished yet because I haven't connected all the nodes, but it's my start. Looking at what I have now as my minimum spanning tree, what's the smallest edge that goes out from any of the nodes currently in my very small minimum spanning tree? So I have D in there and I have E in there. What's the smallest edge going out from either D or E? Sorry, say that letter. Yeah, DB, right? You see it with the 6, I think, because I have a 6, I have a 19, I have a 2, which I've already added, so that's out. I have a 7. So I have 6, 19, or 7, so I'm going to go with the 6. Do you see that? This is the smallest edge going out from either D or E. So I go, great, right? I add that one, 6. Do the same thing again. Smallest edge going out from either D, B, or E, all of them. Now this begins to get hairy, right? As I look at stuff, like, oh, crud, like there's a lot of things to keep track of. So algorithmically, you'd be keeping a sorted list of all the edges that you have, et cetera, but we're just going to stare at it. We're going to use our people skills and just stare at it. Be like, okay. So the smallest edge going out of B is, ooh, BC's 2. That's a good, that might be it, but let's double check. No, nothing out of D that I don't already have is better. Nothing out of E is better. Okay, so we're going to do BC. Right, so we'll go BC. 2. Awesome. Now I need the smallest edge going out of E, D, B, or C. So we're going with, this is the one we're leaning towards? This one here, this 3? Yeah, I think so, because there's a 4 and a 5. Those are both bigger. The 3 is less, the 7, the 19. Yeah, I think it's that one. I think that's the smallest one we have. 3. Great. Now we just keep going. Okay. You want to add CG? Oh yeah, that's a 4. Okay. 4. And then what? Sorry? Well, you want to do BF. Okay, so it's interesting to note that when we did the CG, there was either CG at 4 or BF at 4. We could have done either one, right? Doesn't matter which we do, they have the same weight. So we'll stick with that and we'll go BF4. Okay, now in this particular example, sadly, there was one point of the algorithm we didn't have to do. It's just happenstance by the node that we picked. We didn't do that, not yet in the minimum spanning tree. So you'll probably have one in the example you'll do in just a second. But we didn't do this, the one that's not yet in the minimum spanning tree. And what I mean by that is, if you find the smallest edge and you're looking at it and adding it would connect a node that's already in your tree, don't do it. Right? There's no reason to. So let's pretend for the moment that when I was like, let's pretend, just ignore me, ignore the reality, but let's pretend for a moment that the smallest edge was this one, and it was like, you know, weight 4. Like I wouldn't add that edge because it's connecting B to G, and both of those are already in the minimum spanning tree. So there's no point. That doesn't help, right? That doesn't add to the tree. So I'm only adding in edges that bring in new nodes, right? So in this case, I'll put this one back, right? But okay, we're gonna do a little bit of practice here. We're gonna start with Prim's because that's the one you just did, and then we're gonna go back and do Kruskal's. Okay, so Prim's. use Prim's algorithm on this graph. The algorithm's there on the right, the graph's there on the left, you know, piece of paper or your iPad or whatever. Follow the algorithm. Let's see what we got. I want to emphasize something important here with these. So we have Prims and Kruskals. You're going to work through both. We'll work through the other one in just a second. On assessment 5 or 6, the one that covers graphs. Wait. Yes, 6, the one that covers graphs. Thank you. I was like, where are we at? On assessment 6, the one that covers graphs, you will likely have to do one or both of these. I'll give you a graph and be like, use the algorithm, right? Now, if you pause and think about that for a moment, you'll be like, it doesn't matter which algorithm you use, you get the same answer, right? Unless there's like different minimum spanning trees. So part of the problem is also specify the order in which you're adding the edges to the minimum spanning tree so I can make sure you're working the algorithm properly, right? So when you solve this, like the truth of the matter is you could stare at this picture and kind of draw and be like, you could probably wing it, right? Like you could be like, that F to G is going to be there, that C to F is going to be there, that F to A is going to be there. Like you can wing it as you go. But don't do that because then you won't add things in the right order and like then you won't get the credit, right? Because my goal here is to make sure you understand how the algorithm works, not that you can stare at a simple graph and like whip out the minimum spanning tree by squinting, right? Like because for any graph of any real substance, you would have to use the algorithm, right? Like if I gave you 50,000 nodes, such as homework 6, right? You would need to like be able to run the algorithms. You can't just like wing it, right? So anyway, so my algorithm here. Ooh, okay. Oh, now the hard part is everybody picked a different arbitrary vertex, right? So I don't know. Celine, what was your starting point? C. Okay, you use C. So let's highlight C here just to make sure we're at the right thing. So there, we're going to start at C. Okay, so let me draw my spots. E, C, B, F, G, D, A. Okay, so if you pick C, who's the first edge off? Yep, C to F at 4. Great. Okay, so now I stare. Somebody else, who's next? F to G at 1, right? So off on the side here, just to make sure, C to F, F to G, right? I'm making a note of the order in which I add the edges. This makes sure that the grader knows that I didn't just make it, I didn't just like stare at it and figure it out, that I followed the algorithm, okay? Next. Okay, so I hear FA is a proposal, that's got a 3 out of there. And that seems pretty good. So we'll go with that. FA gets me a 3. Did I hear? Oh, DA. Yeah, that's a 5. So that seems pretty good. What are my other potentials? There's a 15 over here. There's an 8. So 4. Yeah, we'll go with DA at 5. That seems fine. Boom. So GB, well, yeah, that one is 6. That seems pretty good. Oh, yeah, so wait, I forgot DA, GB, okay. And now I can kind of leverage the line in there that says not yet in the MST to know I've got to connect in E, right? So I'm looking at like, what are the edges going into E? What's the smallest one? EF, 8, F, E, right? Done, minimum spanning tree, right? So the two pieces that I'm going to need on my final answer are this and this. This to make sure you got the right answer, this to make sure you use the algorithm the problem said. Yeah, Celine. Oh, great question. Is CF and FC the same thing? Yeah, this is literally just you giving us a hint as what you did. We just verify you did the algorithm. The truth is we're not meticulously grading this. It's more like we're looking at this like, yes, and then we're skimming this and being like, yeah, they solved it in the right order, right? Honestly, I've been known to forgive like random things in here being out of order just because you screwed up, right? You put a 4 in before a 3, like, whatever, you followed the algorithm, I'm fine, right, for the most part. Okay, so that's Prims. Okay, let's jump back. Here's one with Kruskals. So Kruskal's, the algorithm's there on the right. It's the same graph, but like now you're going to do it with Kruskal's algorithm. So go ahead, Kruskals. For this one, I do recommend you build the way that you sort the edges like you write it down. It's too error prone if you try to do it like by hand. You'll tend to miss stuff. Like it just happens. So yeah, make your list of sorted edges and away you go. All right, let's get started. So the first step is to write down all the edges in sorted order. FG, oop. FA, yep, thanks. Sorry, I missed the last one. Oh yeah, FC, yep. DA, okay. Oh yeah, GB, and then DG. Oh yeah, DG. I was gonna miss that one. I was looking at over here at the 8. Okay, so now the 8, EF at 8. Okay, who's next? DF. Oh yeah, no, yeah, I would have messed that up. Not DF. F or EC, right at 12. Then DF. Yep. Did I miss somebody? Oh, I'm not adding them. I'm just sorting them right now. I'm not like adding these edges in order. I'm just making my sorted list of edges so I can run the algorithm. So my first step is make the sorted list. The nice part about building the sorted list is you're making yourself less error prone. You could try to stare at it and pull them out in order, but if you mess up, like I tend to miss edges, like you just saw me do twice, right? And if you mess that up while you're building the sorted list, you'll come back to it and be like, whoa, I missed a 12 and I'm already on 14. You have to fix it. But if you do it in the middle of the algorithm, you just won't even notice. Okay, so now I'm at AG 14, CB, and then CG. Okay, so I've got all of my edges in order. Okay, so maybe what I'll do just to move these down here. That way I can draw my answer in one spot, keep it all on the screen. So E, C, B, F, G, D, A. Okay, so now I start going through. F to G, 1. Okay, boom, FG is done. F to A, 3. Thank you. See, FC, that seems like a good one to add. 4. DA, I think we're still good there. 5. I'm really hoping we get some cycles in this example. GB, 6. Good. DG. Okay, so DG would go here. All right, so if I draw it, it'd be like boop. But that's a cycle, right? It's got a little crisscross in it, but it's still a cycle because it's like, oh, like that gets me back. So I can start at D, go this way, and I'm back. So I don't want to add that. So don't add DG. Yay, we had a cycle example. Okay. EF, that seems good. No cycle. 8. Yeah, thanks. What's next? EC. Yeah, EC would add a cycle. Boom, that would be a cycle. So we won't add EC. DF, that would be a cycle. Won't add DF. Oh, I don't even have to continue. We have a minimum spanning tree. I just started like, oh, all the nodes are now connected. We're good. We're done. Right? Just out of curiosity, is it the same? I don't know if we stare at it. Maybe I'll copy this. We'll copy it down to the other slide just to compare. See if they're the same. Oh, whoops. No, don't take it away. There we go. I think it's probably the same, but let's see. Oops, don't want that. And don't need this piece. Boom. Okay, so do we have the same answer? Yeah, it's the same. That's great. Okay, so now I don't need that one. But so Prims and Kruskals in this for this graph came up with the same answer in both cases. So we're good to go. Now remember, as I mentioned before, you're not necessarily going to come up with the same answer. There could be multiple correct minimum spanning trees, right? So if that's the case, you could come up with different answers from the two different algorithms. which would be really funny to mess with you on an assessment, right? Like I give you the same graph on both and say do it with both algorithms, you get a different answer each time. It really makes you question yourself. If you get to that point, just sum up the edges on both and be like, oh, no, it's just two different minimum spanning trees with the same weights, same cost, so you're good, right? The truth is those graphs are really hard to make. Like they take more effort, and I may or may not do it, so we'll see. But if it comes up, don't like freak out. Just be like, do these two different answers have the same cost? If so, I'm fine, right? And then you're good to go. All right. Next algorithm. So we've done two different algorithms for the minimum spanning tree. I alluded earlier to the concept of shortest path. Let's look at shortest path. So in red, or what I'm putting together, I call this is the shortest path between bedroom 1 and the utility room. Why would I want this? Well, let's say that for a variety of reasons, my apartment has very bad Wi-Fi reception. And the person who lives in bedroom 1 can't get good Wi-Fi, and they say, I need you to run an Ethernet cable. Well, my router's in the utility room, right? So what I want to figure out is what's the shortest path to run an Ethernet cable from the utility room to the bedroom, right? What's the shortest route? I'm going to run it through the same like potential connections that the electricity could have gone through, same idea, holes in the wall or whatever, but I want to know the shortest one, right? And this is it, right? This happens to be the shortest path from the utility room to the bedroom, right? Now there's lots of ways I could have done it, right? I could have gone here, that would have been a way. I could have gone there, that would have been a way, right? I could have gone there, that would have been a way. There's all sorts of different paths I could have used, but the shortest one is the one with the least weight across its edges. It just so happens that this is the shortest path. This algorithm comes up a lot. There's a lot of problems in computer science that are solved with the shortest path algorithm, because in the end, this is an optimization problem. It's given a bunch of data, find the shortest, the best, the least cost, whatever, right? And those problems come up a lot in the real world. Because if you can find the shortest, best, least cost, whatever it is, chances are high that your company just saved money, right? And so the shortest path algorithm is a very useful one. So the classic algorithm for shortest path, zoom this guy in a little bit, it's called Dijkstra's algorithm. Dijkstra was a very famous computer scientist who did most of his work before like we had anything you would think of today as computers. He was really more of a math person, but at the core, he came up with algorithms that are still widely used today to solve a lot of problems. Dijkstra's algorithm is a shortest path algorithm. The concept behind shortest path is fairly simple. If I want to know, going back up here, if I want to know the shortest path to from the utility room to the bedroom, the intuition is that in order to find that out, I'm going to need to actually find the shortest path from the utility room to every other node in the graph. Because it's really not possible for me to find the shortest path from the utility room to the bedroom unless I also know the shortest path from the utility room to the hall. Because if I don't know the shortest path to the hall, then how do I know that the shortest path to the bedroom doesn't go through the hall? You kind of get, this is a real vague intuition I'm trying to give you. But the key observation here is that if I want to know the shortest path from utility to bedroom, I need to know the shortest path from utility to everywhere. And then using that information, I can ultimately find the shortest path to the bedroom. You'll see as we run the algorithm what I mean by this. But that's my intuition. My intuition is that I need to find the shortest path. If I want to know the shortest path from utility to somewhere, I really need to find the shortest path from utility to everywhere, and then from that, get out the final answer that I want. I'm going to find the shortest path from a particular node to every other node in the graph. And once I'm done with that, then I can pick out the individual destination that I want. Okay. Ooh, Dijkstra's algorithm. So here's a graph on the left. And what I'm going to say is that I want to find the shortest path from one node to every other node in the graph. So let's see, did I specify on here? Yes. A, I'm going to start at A in this case, just because that's what my example has. Alrighty. I need two different tables that I'm going to be tracking information with. The first table is called the unvisited list. Unvisited list. the UL in the abbreviation in the little algorithm description down below. And then the other piece I need, the other table I need, is called the distance list, the DL. They're both going to track very similar things, but they are going to be subtly different. Okay. Move this over a little bit just so we can still see it despite the zoom thing. Okay, so we have the unvisited list and the distance list. The unvisited list is going to have 3 columns to it. Or sorry, no, the unvisited list has 2 columns to it. Ooh, okay. The node and the distance, the node and the distance. And in this case, the distance is the shortest path to that node. So the shortest path from A to that node. We're going to start with A. So remember, A is our starting point here. We're trying to figure out the shortest path from A to every node in the graph. So the unvisited list is going to contain nodes and the shortest path I know so far, right? The distance list here at the end is going to contain the same thing, but with 1 extra column. So I'm going to have, let's see if I can get all this in one thing. I'm going to have node. I'm going to have distance. I have something called previous. Okay. In order to get the algorithm going, so this particular chunk of text here is the description of as the algorithm runs. In order to get it going, the first thing I need to do is I need to add 2 entries here. I need to put the entry for A, and I say, okay, what's the shortest path from A to A? This is a stupid question. What's the distance to go from A to A in the shortest possible way? Don't overthink it. 0, yeah, I go to distance is 0, right? You'll see why we need this in a moment. And then I go, okay, the shortest path from A to A is A, and the distance is 0, and previous we'll define in a moment, but it doesn't make sense yet, so we'll get there. Okay, so now I start running the algorithm that's in this paragraph right here, right? Algorithm says, remove the lowest cost item from the unvisited list. Okay, my unvisited list only has 1 thing in it, so I'm going to remove that one. That's the lowest cost item, right? A. So I'm just going to make a little note over here of what I'm working on right now. A, and it's got a distance of 0. Okay, so I'm going to cross that off my unvisited list. So that's the one that I'm working on right now. Find the shortest length of the path from, oh yeah, let's call that current. So here's cur. Boop, cur. Find the shortest path from A to cur. Well, that's in my distance list down there. The shortest path I know is 0, so I wrote that down. Node A is my current node, and the shortest path to A is 0. Great. 3rd bullet point. For each edge leaving the current node, in that case that's A, see if the path going through that node is shorter than any previously known path. Okay, so what I'm doing here is I'm saying, assuming that I got to A through the shortest known path that I could, where else could I get from A, and what would be the total distance to get there? So, for example, I can get to B from A, right? What's the total distance to get to B from A? Directly. 12. Okay, so I'm going to go great. B. I can get to B. I now know that so far, I'm saying I can get to B in a distance of 12. And in the path that got to B in a distance of 12, A was the node I was at previously. This will make more sense as we go along. So I go, okay, great. Got that one covered. Where else can I get from A? Oh, I need to make a note of that up here too in my list. So I can get to B in 12. Okay, where else can I get from A? C, okay, I can get to C. I can get to C in 3. If I go to C in 3, the previous spot was A, so C, 3. Okay, where else can I get from A? E. Boom. E. I can get there in 17. Previous node was A. E, 17. Now I know that at this point it feels like, what are we doing? This feels silly. It'll make more sense in just a moment as we get into the next stage, right? Okay, so what I noticed is that as I went through these, each of these nodes, they weren't in my unvisited list already. and I had never like seen them before, so they all went into my distance list. My distance list is tracking the shortest path I've seen so far to each node. So right now I'm saying the shortest path I know of so far to get to B has a cost of 12. The shortest path so far I know of to get to C has a cost of 3. You get it? What the unvisited list stores is, nodes I still need to process and see if I can build a better path from them. Right, so, okay, so I finished this stage. So I'm gonna be like, okay, great, there's cur is done. Now then, I go through here and I pop off, it says the lowest cost item from the unvisited list. Who's the lowest cost item from the unvisited list? C. C's got the lowest cost, so it'll go great. C. And what was that cost? 3. Okay, C has a cost of 3. Awesome. So now I'm at C, and I say, where can I get to from C? And is getting there any better than what I already know? Okay, so for example, from C, I could go back to A, which would mean that if it takes me 3 to get to C and another 3 to get to A, I could get to A in 6 total. Do you see what I'm saying? I'm not saying this is a good route, just that it is a route. Now, I could get to A by going A, C, A. That would be a route to A. Is that better than my current best route to A? No, it's worse, so I'm not going to do anything with it. I could get to B from C in 2. If it took me 3 to get to C, and it's 2 to get from C to B, that means I know how to get to B in 5. You see where I came up with that? So I'm saying I'm at C. It took me a distance of 3 to get here. I could get to B in 2, so the total cost of B is 5. Is that better than what I know for B? Yeah, that's better. So I go, ooh, this is 5. And the way I can get there in 5 is if I was at, or sorry, not B, if I was at C prior. So say I can get to B in 5, and the node I was at to get to B in 5, before B I was at C, and then it's like, oh, well, where was I at before C? Oh, I was at A. See this? So from this thing right now, I say, oh, I know how to get to B in 5, and I can get there by going from C and from C to A. So my path would be A, C, B. So that's my shortest path known so far. What we just did there is the important, this is the important part of Dijkstra's. Like, I'm at C, cost me 3 to get there. I can get to B in 2, so I know a path to B that's 5. Boom. So now I can say, aha, my shortest path to B so far is 5. When I make that change, I need to run up to my unvisited list and quickly update to say, you know what, B, I used to know a 12, but now I know a 5. That'll come up for us later. So I go, great. Okay, where else can I get from C? I can get to D. I can get to D in like 19. Okay, so I haven't been to D before, so let's add that, D. What's the total cost to get to D if I'm going via C? So I'm at C, it took me 3 to get here, it takes me another 19 to get to D. 20, 22. Did you see that observation? I'm saying I'm at C, it cost me 3. From C, I can get to D. So I know a route to get to D in 22 that goes via C. See what I'm doing? I'm at C. I say I can get to C in 3. Oh, I can get to D in 19 off of that. So I know a path that goes a total of 22 to get to D, and it goes through C. That's what I'm building up. So I go, great. Okay, that covers that one. F. I can get to F in 5. It cost me 3 to get there. So I know a path to F in what? 8. I know a path to F in 8. Oh, I almost forgot. Because I just found a new one, I have to add them to my unvisited list and get to D in 22. Okay, now then, back to F. Zoom out a little bit. So I'm going to say, great. I can get to F in 8 via C. Boom. And I have to add them up here because they're also new to me. Okay, I can get to F in 8. Okay, keep going. I can get to G. And what's my total cost to get to G? 7, because I can get to C in 3, I can get to G in there. So I go, great, G, 7, previous one was C, G, 7. Okay, so I think that's all the nodes from C going out. So now where are we at? I have a distance list. that shows me the shortest path I know of so far to each node from A to each of these nodes. Here's the shortest path I know so far. I have my unvisited list, which is nodes I still need to potentially process. All right, so I go through. I need to pick the smallest node in my unvisited list. Who's that? Oh yeah, C3 is done. I finished off that one. That's one I just did. So who's next? Yeah, G, or no, B. Yeah, B, right? Because B was 12 and now it's 5. So B is the smallest one. So I go, great. B, that has a distance of 5. I'm going to cross it off so I don't forget like I did last time. Okay, so I say, ooh, I can get to B in 5. Where could I get from B? Or where could I get from B? I could get to A if it took me 5 to get here, right? I could get to A in 17. That's not better. Don't do anything with that. I could get to C in a total of 7, 5 to get to B, plus 2 to get to C. That'd be 7. That's not better than I have for C. Don't do anything with that, right? I could get to, so what am I doing? I did that one, I did that one. Who's next? Oh, I could get to F in a total of 9, 5 to get to B, 4 to get to F. Is that better than my current F? Nope, not better. So I don't do anything with that. I could get to D in a total of 11, right? 5 to get to B, 6 to get to D, so I could get to B in a total of 11. Is that better? Or sorry, I could get to D in a total of 11. Is that better? Yeah, that's better. So boom, this becomes 11. And that was if I was at B previously. Because I updated that, I have to remember it updated in my unvisited list. Okay, boom. That's good. Who else? So we did here, 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 and here. Okay, we finished. We've processed all of B, right? Great, so cross that one off. Who's next? So the next is the lowest cost item in my unvisited list. G, okay, so let's process G. So I'll say G, 7, cross that one off. I can get to G in 7. Where else could I get? Well, I could get to C in 11, because if I can get to G in 7 and get to C in 11, that's not better. I could get to F. If I can get here in 11, I can get to F in 17. Is that better? Nope. So nothing, right? That didn't help me. So I go, okay, fine, I'm done with that. G7. Who's next? F at 8. Yeah, okay. So I can get to F in 8. Where else can I get from F? Well, I can get to E, right? I'm just going to walk through them counterclockwise. I can get to E here in, see, if it's 8 to get to F plus 7 is 15. I can get to E in 15. Is that better? Yeah, that is better. 15. And that's if I'm at F. Okay, so I need to update this one with 15. Perfect. Okay, who else? I can get to B in, see, I can get to F in 8 plus 4. I can get to B in 12. Nope, that's not better. I can get to 8 plus 5, C in 13. That's not better. 8 plus 6 gets me 14. I can get to G in 14. That's not better. Okay, so I'm done. I finished processing F. Who's next? D at 11. D, 11. Okay, so I'm going to process D at 11. So I can get to D in 11. Where can I go? I can go to B in 17. No. I can get to C in 11 plus 19 is 30. No. I can get to E in 13. That's better. I'll take it. 13. And in order to get there, I had to be at D previously. So E becomes 13. Boom. And that's it. I finished processing D. And now, I mean, I can go through it for E, but since E's the last one, like, I can check it, but like the fact that he's last means I'm not going to be able to do any better. But so if I can get to E in 13, I could get to D in 15. No. E in 13, I could get to A in 17. No. E in 13 means I could get to F in 20. No. So I'm done. Right. So now, do I have my answer? Yes. This list now contains the shortest path from A to every node in the tree. But how do you pull it out? Well, first of all, what's the cost? So let's do the hardest one. I want to say A. Okay, so let's say I want to know A to E. what's the cost of the path from A to E based on the distance list? 13, yeah. So I know that there's a path from A to E in 13, but what is it? We have to work it backwards. So I go, okay, I'm at E. If I go backwards from E, then I go to D, right? Because E tells me here that the previous one was D. If I go backwards from D, I get to B, right? If I go backwards from B, I get to C. And if I go backwards from C, I get to A. So this says that the shortest path between A and E is A to C, C to B, B to D, D to E. So there it is. And when I stare at the graph, I'm like, yeah, that is the shortest path, right? Look at this. These are all tiny little numbers compared to bigger ways. There's a more direct way that costs more, but there's shorter ways as well. So that's Dijkstra's shortest path algorithm. So now, with just this distance list, you could pull out the shortest path from A to any other node in the tree or any other node in the graph, right? Okay, we'll stop there. We will build some graph stuff in Eclipse next class.